So we just saw that we can predict the geometry of simple molecules, ones that have central atom. We can simply extend that and predict the shapes or geometries of larger molecules. So basically what happens is that we will look at each of the inner atoms in a Lewis structure. Inner I mean they're the ones that are bonded to more than one thing. The hydrogen here are called terminal. They're only bonded to the one thing and that's it. So they terminate a bond. They terminate the molecule. So what we'll do is look at each of these carbon atoms at different times. So we'll start with the one on the left and then go to the one in the middle and the one on the right. And we will treat them as the central atom. And we will count the electron groups around them. And from that, we will determine the geometry. So if we look at this first carbon, around it there's 1, 2, 3, 4 bonding groups and no non-bonding groups. We saw that if we have four electron groups, the electron geometry is tetrahedral. And since there's no non-bonding groups on the carbon, the molecular geometry is also tetrahedral. Looking at that, so we would predict that to be tetrahedral. Looking at that second carbon, the middle one, it also has 4 bonding groups around it. So we would predict that would be tetrahedral. And then that last carbon has 1, 2, 3, 4 bonding groups around it. Notice we count a bond between two atoms for both atoms because the electrons are shared. So that last carbon also has 4 electron groups around it. So it is tetrahedral. So if we want to show this, we could draw it, or we're going to look at a ball and stick model. We can see that the carbon on the left, it's got the 3 hydrogens, 1, 2, 3, and then the bond to the middle carbon. And this is the middle carbon. It's got a bond to the carbon on the right. It's also got bonds to 2 hydrogen atoms, right here and right here. And then the carbon on the right has bonds to 3 hydrogens, and it's tetrahedral. So we can see each of these is tetrahedral in their own rights. But this gives us a way to kind of depict what the molecule will look like using the theory we just did. So if we do this again for this molecule, ethene or ethylene, same thing, just we name it a couple different ways. We're going to look at each of the carbons. The carbon on the left, it's got 1, 2, 3 bonding groups. Remember, 3 bonding groups are trigonoplanar. Okay, and the carbon on the right has 1, 2, 3 bonding groups around it and no non-bonding groups. So it's also trigonoplanar. Let's see if I can make that a little bit nicer. Trigonoplanar. So both of those are trigonoplanar, meaning they've got 3 bonding groups that are equally spaced around each of them. If we look at that from the top, since it's planar, it's flat. I've got the carbons, and then I've got each hydrogen. And you can see the left carbon is trigonoplanar between the 2 hydrogens and the bond to the carbon. And the carbon on the right is trigonoplanar because of the 2 hydrogens and the bond to the carbon. If we do the side view, because it's planar, it's flat. All right? So we'll do this one more time. I've got 3 inner atoms, 2 carbons and an oxygen. The carbon on the left has 1, 2, 3, 4 bonding groups and no non-bonding groups. So that carbon is tetrahedral. in both the electron geometry and the molecular geometry because there's no non-bonding groups on it. That middle carbon has 1, 2, 3, 4 bonding groups around it. No non-bonding groups, so it's also tetrahedral. And then finally, the oxygen has 1, 2 bonding groups and 1, 2 non-bonding groups. So 4 total groups, except in this case, it's got some non-bonding electrons. So the electron geometry is going to be tetrahedral, while the molecular geometry is going to be bent because of the 2 non-bonding groups. Okay, both the other carbons, both the electron geometry and the molecular geometry are tetrahedral because there's no non-bonding electrons in either carbon. Okay, so we could go ahead and draw this if we wanted to. I'm not going to do that, but you can see how we're going to predict the structure of larger molecules from simply looking at each inner atom.